Okay, example 1, our directions are to state intervals on which the function g, which is graphed here, is continuous. And then where the graph is discontinuous, we have to identify the discontinuities, either a jump, asymptotic, or removable. We'll talk about what those look like on the video here. A continuous interval is just an interval in which there's no breaks. So every time there is a break in any way, shape, or form, like this, or just a hole in the graph, or maybe it goes straight up or straight down, so it's hitting an asymptote. Each of those represents a break in the graph, so it represents a point where it's discontinuous. What I care about when it says state the intervals, it states intervals of x. So we're worried about the x-axis numbers. Every graph starts at negative infinity if the arrow points left. It ends at positive infinity if the arrow is pointing right. And every x in between has to be accounted for. So this graph, it's got an arrow pointing left, which implies it stays unbroken all the way to negative infinity. The first breaking point happens here, which is at negative 6. The second breaking point is here at negative 4. The third breaking point is here at negative 2. Fourth breaking point here at 0. Fifth one here at 1. Sixth one here at 4, and that's it. Everywhere else is continuous, meaning there's no breaks in it. So when I'm identifying an interval of continuity, if we just focus on this part of the graph here, it ends in an closed circle there. Not because I filled it in, because it started off that way. When I identify an interval, I want to start somewhere and go to the right and end somewhere. And then I have to make a decision whether I should use parentheses or brackets based on what I'm looking at. Infinity always is parentheses. If I stop or start at that closed circle, that's going to be a bracket. So this is ending at a closed circle, so negative 6 is closed circle, so I'm going to bracket that. The next interval starts here with an open circle and ends here with an open circle, and it's continuous all the way through. So it starts at negative 6, it ends at negative 4. The starting point is open, so we put a parentheses. The ending point is open, so we put a parentheses for both of those numbers. The next interval starts at negative 4, ends at negative 2. Open circles for both of those also. Continuous everywhere in between. So I'm starting at negative 4, ending at negative 2. Open circle at negative 4 on the left. Open circle at negative 2 on the right. So parentheses on both of those. Next interval starts here with a closed circle, and it goes straight up. So it never ever touches 0, just going straight up. So zeros are acting as an asymptote, x equals 0. So my starting point is negative 2, my ending point is 0. The starting point this time has a closed circle, so I'm going to bracket the negative 2. The ending point doesn't have any circles, but again it goes up, straight up. It's asymptote there, so I'm going to put a parentheses because we never have any values at the asymptotes. Next interval starts here. This is going straight down, and we're going up to this open circle right here at 1. So the interval starts at 0, ends at 1. Again, an asymptote doesn't actually take on a value there, so it's like an open circle. This is actually an open circle, so we get parentheses at both of those. Next interval starts here with an open circle, ends here with a closed circle, and everything in between is continuous. So it starts at 1, goes to 4, open circle at 1, parentheses, closed circle at 4, bracket. And the final one starts here with an open circle and continues on this direction infinitely. The arrow says it goes all the way to infinity, so we're starting at 4, ending at infinity. Open circle at 4, parentheses is always used to infinity. So there's my intervals of continuity. Every one of those intervals represents a part where the graph's continuous. Starting at negative 4, ending at negative 2, the graph is continuous. There's a break at negative 4, negative 2, and so on. If a graph has a bracket, that means it's continuous from that direction. So the red one's continuous from the left. This orange one's continuous from the right. Okay, that's words that you might see in future examples. Once you've established all the intervals of continuity, it says to identify the discontinuity as jump, asymptotic, or removable, and where the graph is discontinuous. So the graph's discontinuous everywhere there's a break. So each one of these endpoints, so negative 6, negative 4, negative 2, 0, 1, and 4 represent breaks in the graph. Each one of those represents a discontinuity. So we want to have to identify each of those. So x equals negative 6, x equals negative 4, x equals negative x equals 0, x equals 1, and x equals 4 represent the 6 discontinuities in this graph. And I need to identify them as a jump discontinuity. This is what jump discontinuities look like. There's a dot and then a vertical distance between the other dots. So whether it's open circle, closed circle, this one jumps with one open, one closed. This one jumps with both open. All right. It doesn't matter open or closed, just so long as there's a dot somewhere and there's a dot vertically positioned from that. That's what a jump discontinuity looks like. So that's a jump. I'm fine with just putting J, A, or R for these. So J for jump, A for asymptotic, and R for removable. The next one, -4. This is what a removable discontinuity looks like. The graph is continuous except for this hole in it. The graph has the same limit on both sides. That's a removable discontinuity. -2, we got another jump. The only asymptotic one we have here is this. If the graph goes straight up or straight down, we're looking at an asymptote. That would be an asymptotic discontinuity. Once again, this is a jump because it goes from one value to another. The same thing here. For one value of y, it jumps to a different value of y. So that's what we look for the other part of this. And one thing that I noticed in the homework as I was looking at it, how to handle it. Suppose we got our stuff going on here. Let's just say I've got a closed circle there. Let's say the graph does something like this. And then from the other side, let's say it's looks like that. In fact, let's move this over a little bit. Okay, so looking at this discontinuity here, obviously there's a break here at -3. And it goes to an endpoint, but then it goes, looks like an asymptote on the other side. So you could consider that either a jump or an asymptotic. I'll take either one. So at x equals -3, you might even put both. So it's jump and asymptotic. Jumps like a jump one, but it's got an asymptote on one side. Looking at this one, the next interval, you see a dot here, but it's closed, and then you see an open circle here at +3. You might be tempted to go -3 to 0, 0 to 3, but this closed circle means that the graph doesn't stop. It just changes its look. So it kind of made an abrupt switch. But the continuity is there all the way from -3 up to 3. Parentheses, parentheses, open circle because it's asymptote, open circle because parentheses because of an open circle. Again, the graph itself is not discontinuous there because it doesn't have a hole, it doesn't have a break. It does make an abrupt move, but it's not discontinuous. So if I was trying to identify discontinuities, this is discontinuity, jump or asymptotic, or both, take your pick. There's a discontinuity here at x equals 3, that's a removable variety. The intervals will be, this will be 3, infinity for this one. This one here will be -infinity, -3, bracket on the -3, parentheses on the -infinity. Other than that, I think most of it's going to be pretty straightforward. So hopefully that'll make enough sense.